Welcome to video 12. In this one, first we'll make the points where the cross braces meet our squares, and then we'll separate our squares into two different groups, one group that receives cross braces and one that won't. So let's go back to the article we've been referencing. Now that we have our squares, we have this length L. This is just the length of one segment of a square, and with L we can find out where the cross braces meet the squares.
So one page up on the article that we're referencing, there's this equation here. This top sentence, this top part of the sentence is just describing the thickness of the squares relative to the cross braces, and we'll get to that later. But what we need right now is this equation, S equals L divided by root 2 plus 2, and that's going to tell us where to make the intersections of our cross braces and the squares. So back on our Grasshopper canvas, we can grab these four components, since these are the four that I think we'll need in this next round. So I'm going to press Alt to copy these and bring them down to a new line. And we can hide all of the wires. And while that equation is fresh in our mind, let's write it on the Grasshopper canvas. So I know we have a root 2, so let's get a square root component. By typing square root, and since this component takes in a number and gives you the square root, so x is your input value and y is going to be the square root of that. So let's get a panel with 2. I'm just going to do two slashes and the number 2 to get a panel with a 2 in it. So now we have root 2, and then if we look back here, we need root 2 plus 2. So let's get an addition, and root 2 is going to be A, and 2 is going to be B. So what's coming out of R is root 2 plus 2, 3.414. And back here, so the length from this node where four squares intersect to where this cross brace intersects is L divided by root 2 plus 2. So we're going to set L to 1, and that way we can easily scale it to whatever size our squares actually are. And so we're going to do, instead of L divided by root 2 plus 2, we're going to do 1 divided by root 2 plus 2. So back here, let's get a 1 and a division component. Just type slash for division. So 1 divided by root 2 plus 2, and this is going to be the parameter where that first intersection is. And we can see that we have two intersections. We have one here and one that is equal distance from the end. So if L is 1 and this is 1 divided by root 2 plus 2, then this is just going to be 1 minus 1 divided by root 2 plus 2. So we're going to do the version that is a distance from 0 and the version that is a distance from 1. So to get our second parameter, we'll go back here and get we can just use this 1 again, I guess, and get a subtraction by clicking dash or by pressing dash. And we have 1 minus this, and now we have our 2. Let's get a panel to see what these are. These are our two parameters. Where along a length of 1 would our two intersections be? They'd be at 0.292 and 0.707. So let's merge these together. The merge component, let's put the small one first and the larger one second. And let's zoom back in here. And I'm going to pull these down just a little bit for a minute. And let's grab our polylines dependent. This is a flattened list of all of our squares. And just so we can see what's going on, I'm going to grab just one square. So I'm going to get list item, and that's by default 0. So this is just pulling out the first square in that list. So let's just look at this square for now. I'm going to get an explode component. And so this is going to give me the segments in that square. And if I get list item again, this will give me just the first segment in that square. So this is just the bottom line in that square. And then if we get an evaluate curve component and we plug this in, remember that I said we were going to pretend that the lengths are all 1. The way that we can do that here is right click and go to reparameterize. And so regardless of the actual length of this curve, this line-like curve, it's going to treat it as if this point is is at 0 and this point is at length 1. And so as we move along, as we increase from 0 to 1, we go further along this curve. And this input is asking for parameters. And so if we plug our two parameters that we made from the equation into this parameter input, we get our 2 points. This is where the cross braces should be intersecting this line. And if we go back here, that looks about right. And so that's nice that we can get just one line, but we need to get all the intersections along this square at once. So instead of just getting these two for the bottom line, we need 2 here, 2 here, 2 here, and 2 here. So that'll be 8 points total. And so we don't want just 2 parameters. We're going to need 8 parameters, and instead of this line being 1, we're going to pretend, or we're going to reparameterize this entire square. Since it's already one polyline, we can plug the whole polyline into here. And then we need some new parameters because these aren't quite right if this whole thing is 1. These parameters won't work if this whole thing is 1. And I'm noticing something else I may have done wrong or forgotten. And it looks like we only have 3 segments on this polyline and we need it to connect back down, and so I may have forgotten to put true on the polyline component. The Boolean input needs to be switched to true so we get full squares instead of just the first 3 segments. And so I'm going to go back up here to our polyline component, and I did forget that. So this says close polyline. Right now it's set to false, but we need this to be true. So you can either right click and go to set Boolean true, or you can get a Boolean toggle and double click it to switch it to true and then plug that in. Either way, now we have complete circles, and I'm going to hide this again, and we can go back down here and we can see that our 2 points aren't where we need them to be because we need 8 parameters instead of just 2. So how do we make these 2 parameters into 8 parameters that are falling on the same points for each line segment? So I'm going to plug this back in just so we can see where the correct parameters are, or where the correct points according to these 2 parameters are. Instead of setting this length to 1, we're setting the entire square length to 1. So first let's pretend that if this length is 1 from here to here, then this entire length is going to be 4. Then if this parameter is, let's see what it actually is by getting a panel, it's 0.293, then this parameter, if this whole length is 4, this one that's equivalent to this one over here, but on the next segment, is going to be 1.293. And up here it's going to be 2.293, and over here it's going to be 3.393. Same thing for this one. This one will be 0.707, this one will be 1.707, this will be 2, and down here will be 3.707. So the first thing that we can do is put each of these into their own branch by right-clicking on this output and going to Graft, and then we can simplify that so that we have a branch 0 with 1 number in it and a branch 1 with 1 number in it. Then let's duplicate all of these numbers 4 times. So there's a duplicate component, a duplicate data component. Just type duplicate and it should pop up. And this is the data that we want to duplicate, and we want to duplicate it 4 times. And so now what is coming out of here? We have one branch with all of the first parameters and a second branch with all the second parameters. I'm actually going to simplify this again. So that goes to 1 and that goes to 0. The simplifying is more for organization and understanding how to align different branches. It doesn't always have an effect on the outcome. Sometimes you won't want to simplify, but very often it's a good idea, just so it's easier to read. So with these parameters, we want to add 0 to this one because this one's where we need it to be. We need to add 1 to this one, 2 to this one, and 3 to this one. Same goes for these 4. So let's get a series that starts at 0 and goes to 3. So 0, 1, 2, 3. And we can do that with the series component. Start at 0, that's already the default, which is good. Step up by 1, already the default, that's good. And we need 4 items. So this has 4 locally defined values coming out, 0, 1, 2, 3. That's exactly what we need, and so let's add these together. Addition. And now what's coming out of here? So this is what we want. 0.292, 1.292, or 293, 2.293, and 3.293, and the same goes for these second ones. But what we're going to do is instead of making this length 1, we're going to make the entire square length 1. So right now, this entire square, we're assuming the length is 4. But if we just divide all of these parameter numbers by 4, then those will be the correct parameters. So I'm going to get a division component, plug this in, and I'm going to get 4 on a panel again. So everything's divided by 4, and we'll check the output. These look about right, but we'll have to check them to make sure. And we can see here again the branch is getting a little more complicated than it needs to be. The branch numbers, we have 0, 1, and 0, 0. So if I right click and go to simplify, then I just have 0 and 1. So when we apply these to all the different squares, each square is going to be its own branch, and so each square needs to get all 8 of these. And if we flatten this right now, then the order is going to be this parameter, this parameter, this parameter, this parameter. These first 4 in this first branch will be the first 4 items in the list, which would be this one, this here, up here, and down here, or over here. And it might be easier to have this be the first one, this the second, this the third, this the fourth, and so on and this one will be the 8th. So to do that, before we flatten this list, let's get a flip matrix component. And so now instead of 2 branches with 4 items each, we have 4 branches with 2 items each. And it starts here and goes to this one, then the next branch is these 2, the next branch is these 2, and the last branch will be these 2. And so now we can flatten this list, and they're in the correct order. This would have worked fine without flipping the matrix, but it's a little more organized this way. And let's plug these parameters into our parameter input, and instead of just using a single line, let's use the entire square. And now we have all of the intersection points where the cross braces are going to be meeting this square. And so it works for one square. Does it work for all of them? It should, but it won't if we just plug this in as a list. We need all of these to be in their own branch, so each branch will take in all 8 of these parameters. And so instead of just reparameterizing, we need to do 2 things. The second thing is graft. And now when we grab this and plug it into our evaluate curve component, it'll do the same operation that it did on one square for every square in the tree. We don't need this list item anymore, and we can clean this up a little bit. I'm going to group this, Control G, change the color, and I'll call this parameters for cross brace. Parameters for cross braces, and we'll put that there. Move all of this down a little bit. So this can go over to the left, and we'll move all of this over a little bit. In this second part, we can also group. I'll delete that for now. Control G, change the color. Parameters for full polyline squares. And we can pull this over here. And next we see that this pattern alternates. So this square is different than this square, but the same as this square. So we have a 0, 1 pattern going in either direction. So 0, 1, 0, 1. And if 1 is everywhere that the cross braces exist, 0 is every open square. So the next thing we get to do is differentiate these squares based on this 0, 1 pattern. And let's move to a different surface just for the heck of it. Let's go up here and let's put in the curved surface. Then back down here, we need to grab all the even number squares. So if we get a list item, and it looks like it's starting over on this side, so I'm going to rotate around. And I'll get a number slider between 0 and 50. We want to grab 0, not 1, 2, and so on 4. Looks like this one is 13. So that's good because this is going to be grabbed, but since this is odd, we won't take this one, which will give us the same 1, 0 pattern on going up as it does going horizontally. So to do this, we need to make a series that contains 0, 2, 4, 6, 8, and so on, all the way up to however many squares we have. So let's start by getting a list length component. And this tells us that we have 52 squares on this curved surface. And we only want to grab half of them at first. We'll grab the other half later. So let's get a division component and a 2 because we're going to divide by 2. So we're going to divide 52 by 2, and now we have 26. So we'll grab 26 squares, all the even squares. To make a series component, let's get the series component. This is going to be our count number. We're going to count 26 times. Each time, instead of going the default 1, we're going to go 2 because we need all the evens. And so this series is putting out 0, 2, 4, all the way to 50. And since the last index is 25, we know that there are 26 items. If we hover over, we can see it says 26 locally defined values.
By the way, if this number were odd, this count input would round up. So if we plugged 39 in here, divided by 2 is 19.5, it would round up to 20, and the count would go to 38. 0, 2, 4, 6 all the way to 38, which is good because that would be the last index in our list if we only had 3 rows here, for example.
So we're not actually going to grab the squares. What we'd want instead is these points that are on these squares. So I'm going to delete this panel and bring this over here. We don't need this anymore. And I can use the list of numbers that we got from here, and instead of using the list item component, we're going to do a similar thing but for branches. And this component is just called branch, tree branch. And so this is our tree. We need to simplify it again. And if we get a parameter viewer just to see what's inside, you can see that there are 52 branches, and each branch is labeled like this. And so curly bracket 0 end curly bracket 1 end curly bracket. So that's all of our branches all the way to 51. And each branch n equals 8. Each branch has 8 points in it. And so this is the tree with all its branches, and we only want the branches from this series component. And so these are going to be our path inputs. And so parentheses 0 end parentheses, or curly bracket 0 end curly bracket, this is a path. That's a path to that branch. So if I were to write this in a panel, I could plug this panel in and it would only give me tree branch 1 or tree branch 0 coming out. And you can see that here. So if you're going to specify these with a panel, you do need to use the curly brackets. But if we bring it out of this series component, this component will automatically convert it and give you the curly brackets. So we can just plug it in like that. And we have all of the even branches. And it looks like we have more than we need to, but this is because there's overlap obviously here. But you can begin to see the pattern if you look at the edges. This is a 1, a 0, 1, 0, 1, 0, and so on. And now we need to do the same thing but for the odd branches. So I'm going to pull this list length over here a little bit, and let's group this and call it get even branches. Control G, get even branches. And let's make another group with get odd branches. So let's get a series component again. And this series is also going to jump up 2 numbers each time. So it'll go from 1 to 3 to 5 and so on. And we don't want to start at 0, we want to start at 1. So let's get a panel with a 1 in it, plug that in. And the count is going to be the same because there will also be 26 odd branches.
Or there might be 26 odd branches, there might only be 25. There might be 1 fewer odd branches than even branches in some cases. Since we started counting with even branches, if it ends on an even branch, depending on the number of rows and columns.
If this last square is even, then we have 1 fewer odd branch. If this last square is odd, then they're the same. So in order to make sure that we get rid of all the extra odd branches that we might have selected, let's get a smaller than component. And we'll plug this series into the smaller than component, and we'll make sure that every number coming out of here is actually smaller than the total list. So the list is 52 and the last item coming out is 51. So these are all fine, but in the case that we had an extra one, this will call the end. This will call the last branch number. If we get a call pattern component, and this is going to be our pattern, these are all true for now, and so this will keep everything in the list, but in the case that there's an extra one, this will call that extra one off. And let's get another tree branch component, and instead of using our evens, let's use our odds, and let's pull all of this down here and make a group that's called grab odd branches. And now we have two separate trees, one with odd branches and one with even branches, and so now we can make our two separate patterns based on our 0, 1 pattern that we see here.